So it's 2 o'clock and let's get started. You've just heard Robert telling you about the new advanced distributed SQL features we're introducing here at InterSystems, or working on here at InterSystems. And in the next 40-45 minutes, I'll give you, as deep as possible in this limited time, technology dive and what exactly we're doing and what you can expect from this piece of technology. Again, about myself a little bit. My name is Anton Umnikov. I'm a senior sales engineer based in Toronto, Ontario. I've been with InterSystems for 18 years, believe it or not. Was always working in the areas that demand high performance, high scalability work with InterSystems' largest clients. And for the past year, about year and a half rather, was immersed in these new developments our guys at Cambridge actively working on. So, a little agenda for today. We'll talk about high-level architecture. We talk about building blocks, what let us build this distributed SQL system that easily, that efficiently. We examine how basic operations, such as insert, select, working in this architecture. We talk about deployment scenarios, like how you would deploy this kind of machinery, either in the cloud or in your test lab. And last but not least, very important topic, and Robert kind of alluded to that with his use case example, is how you join multiple tables that might or might not necessarily be local to a particular node. So, first of all, a disclaimer, it's work in progress. Like a lot of things you would see, including terminology, might change in the future. So we use term shared nothing and sharding kind of interchangeably. On the next slide, I would explain you the difference, but why do you need such an architecture? Again, shared nothing as a term not invented at InterSystems. If you look at Wikipedia, the definition would be a computer architecture that no node shares CPU, memory, and storage with any other node of the system, right? Most of you probably know that InterSystems for years had distributed technology called TCP, Enterprise Cache Protocol. Enterprise Cache Protocol is a great technology, but it provides you scalability for memory and CPU, not for storage. And memory, again, only to the extent of the memory you have on your database server in typical ECP architecture. Why storage is important? Like, first of all, if we move into higher and higher scale, efficient storage became more and more expensive. Like, we're not talking about storage that's embedded in your computer or on your server in a rack. We're talking about dedicated arrays, and price tag goes up and up and up as you grow the system. Least obvious, but way more important from performance standpoint, is if your indices would fit in memory. So we're talking about tables that are terabytes and terabytes in size, right? If you keep adding to the end of the table, inserting to the table itself is fine because the tail of the table is always cached in memory, and occasionally if you need to query the whole table, you're kind of expecting delay associated with disk reads. But inserting to the table itself is fine, right? Because the area that you insert in data in is always cached in memory. Now, index, on the other hand, then you add in the table, you add in to the end of the index, to the end of the table, then you add in data to the index, and you're doing that if your table index. You, by definition, insert in data into random places of this B tree that index is. And again, at the moment your index overgrow your memory, like you are in the situation where to make an insert into the table, you have first to pull the block of data from the disk. And if you look at your performance, the response time goes like this, like falling off the cliff. Because to make an insert into the table, you need to physically read data from disk. Right? So architecture where you have one big table on one storage node essentially would not scale past the point where your index doesn't fit in memory anymore. So we need a different architecture. So the architecture we use and we implemented is called sharding. Sharding is the architecture where you get one big table, pick a sharding key, and distribute data across your shard nodes based on the shard keys. And within every shard node, you have table that the same table with the same definition that contains only the rows that belong to a particular subset of sharded keys. Right? So the table on the node is essentially smaller, the indices on the node is essentially smaller than the combined mega table. Right? Sharding, in fact, is a just subset of one of the use cases for shared nothing architecture. For instance, Apache Spark or Hadoop would also be shared nothing architectures, but they have nothing to do with sharding. Right? And again, work in progress terminology might change. So in my slides, you would see terms shards, sharding, and shared nothing using interchangeably. Before we continue with the slides, let me do one thing. Right? I have virtual machine here, and I'll just start the deployment of shared nothing cluster. So basically what's going on in that virtual machine right now is I'm literally deploying within the single virtual machine cluster of 3 nodes, master, and 2 shards. Right? So how do you interact with shared nothing? Right? Again, Robert talked about alternative data models and so on. What we have right now is SQL. And what's very important to understand, it's the standard SQL, the only extension to SQL syntax that we have as it relates to shared nothing is this shard attribute to your create table. So at the moment you create table, you're saying, hey, by the way, this table is sharded, distributed across all my shards. Optionally, you would specify shard key. All the rest is everything you know about SQL still applies. Like everything you do in standard cache SQL would be working on shared nothing as is. Right? So full SQL support without any limitations. Again, as you interface to shared nothing, you have SQL. And speaking of building blocks, we have them, and we had them on Works for many years already. It's parallel SQL machinery and ECP machinery. So let's examine those a little bit more details. If you compare regular SQL to parallel SQL within a single instance, right? In regular SQL, you have one worker process that accesses all the data it needs and delivers results, right? So even your machine has 24 cores, you still utilize in a single process, single core to process and deliver results. If you're running in parallel SQL mode, you have 2 kinds of processes. One is the master that defines the plan and distributes this plan to worker processes. And worker processes, based either on the range or union condition, divide the work in the chunks, process that individually, and then set aggregated results back to master process. That's what's going on in a single instance. Very similar thing going on in the shard system, right? Though those worker processes would be remote processes on the shard, and master would be your aggregator. Right? ECP. Again, ECP been at Works at InterSystems for the past 20-something years, right, including their predecessors. Simplified, it's a distributed global buffer or cache. Right? So what happens if a process on app server 1 requests the data? Data most likely sits on the disk on your database server. So database server would bring this data to its local cache, and then it would bring the data to the cache of app server. Looks fairly simple and straightforward, but if you think about more complex scenario there, this cache, this block would be on more than one app server, and one of the app server decides to update the data, right? And very sophisticated, very complicated machinery would kick in and to make sure that all the nodes has either latest version of the block or block is invalidated, and so on and so forth, right? Though this is the technology that works and that runs some of the biggest cache deployments we have so far, right? And again, typical architecture would be you have dedicated database server and multiple app servers, right? In fact, we're not limited to that architecture, right? You can connect any server to any server in any direction, and in fact, it can be bidirectional connection between two databases on the servers. Typically, it's transparent to the application. We just remotely mount in the database, and cache and ECP would do all this magic underneath, but it doesn't have to be, right? You can use extended global reference the same way you do that here, accessing from user namespace global in a sample database. The same can be done with ECP, and this is what we would use internally to deliver the data where it should be for processing, right? Again, the picture that you saw on a previous slide, it's a typical use case for ECP. It's not what we're doing within sharded architecture, but nevertheless, ECP is one of the fundamental technologies that enables what we're doing in sharded architecture. So let's talk about basic operations. If we are doing insert into the sharded system, and again, here 2 shards, but picture 20, 64, whatever number of shards you may need here. So record is received by the master. Master calculates the hash function based on the shard key, and based on this hash function, it identifies to which shard this record belongs. It sends the record to the appropriate shard, and shard does regular insert into its own subset of the table, right? That's nice and straightforward. Things get a little bit more complicated than you do in update, delete, especially when you have where condition in your DML operation, but like basic architecture is like this. If you're doing bulk insert, like this one-by-one insert where master identifies where data belongs, kind of bottlenecks you at the master level. So where we're moving with that, and what we have right now as a bulk loader machinery works differently. It does connect to the master, but the only reason for bulk loader to connect to the master is to get the shard configuration and shard function. Then it connects directly to the shards, and record by record calculates this hash function, identifies to which shard record belongs, and directs this insert directly to the shards. We have dedicated session, big load, massive parallel data ingestion, dedicated exactly to this piece of machinery. Right now, it's a standalone application. We will be introducing that as a part of regular JDBC drivers. So you basically connect to your JDBC or ODBC driver, stream the data in there, and it would do this magic by itself, right? And the like 4th step, obviously, like regular insert into sharded tables on the shard. So select. Very similar to parallel SQL. Master would parse the statement. It would prepare substatements to send it to the shards. Shards would reach to the data that's local to the shard, calculate the partial results, send it back to the master, and finally master would aggregate these results and deliver the final results to the requesting client. So, from what we know so far, we can kind of speculate about good and not so good use cases for shared nothing, right? The very good use case for shared nothing is you process a lot of data on the shards and return few records back to the master, right? This kind of, we minimize the effect of overhead of this sending data back and forth, right? Aggregates, filter against non-shard keys, and so on, right? Initial version of this presentation contained not so good for the process view, return view, like single row select. But I was rightly corrected that it's not so good if you have one client doing that. If you have one client requesting one record after another by unique key, yes, you have this overhead of going back and forth through shared machinery. But as your number of clients grow and you're doing a lot of these kind of requests, like the benefits of scalability of sharding like totally overwhelm the additional expense of going back and forth for shards and master. So again, it would be good at high scale and high scale only, not for single user scenario. What would be ugly is select star from table, because you're doing nothing but sending tons and tons of data through master to shard. But again, if you'll think about a high scale scenario, like in the sharding architecture, there's a good chance that the whole table, all the nodes would be already in memory. So like you're literally fighting network traffic instead of disk traffic in case of a single machine. Right, joins. And Robert alluded to that. That's very complex. That's kind of holy grail of all this distributed architecture. And we're doing that beautifully, right? We have a special part of our talk just dedicated to joins. Now, let's talk a little bit about deployment scenarios. So again, basic architecture, you have one master and two or more shards, right? In fact, we expect people to deploy dozens, maybe even hundreds of shards there. Master is shard, there's a role that assigned not to machine or not even to the instances, they are assigned to namespaces. So in theory, you can have perfectly valid shard configuration within a single instance of shared nothing, right? Makes no sense technically, but you can if you want to, right? The more reasonable configuration, that's exactly what's being deployed right now, it's probably already done, is having master and shards as separate instances of shared nothing within virtual machine. That's already perfectly valid for testing, for learning, for you can analyze traffic that goes between machines and so on and so forth. But again, that's not your production configuration. Your production configuration most likely would look like this. You have either dedicated machine, or more likely that would be instance in the cloud that hosts single instance of shared nothing and plays the role of either master or shard, right? If you want to, I don't know why you would, but let's imagine you have a good use case for that. You can have 3 machines with 2 sets of shared nothing cluster deployed within them, right? Use case you may think of, you have totally different workloads during the day, during the night, right? There is no need to deploy 6 machines or 2x machines. For that, you can reuse the same machinery, the same configurations during day, during the night. We have shards that provides you horizontal scalability, pretty much unlimited for all the tasks that's going on shards. What about master? If you have a lot of users, and again, from the test we're doing, a lot starts from like 40, 50 right now, might be pushed either direction down the road. But you can scale out your master, separating it into data server and multiple app servers. So pretty much these three servers now play the role of your master. So all the heavy lifting distributed on shards, you keep distributing them on shards, but if at some point your master became the bottleneck, like there's a way to horizontally scale that too. Okay. Something, again, work in progress, but what we're working on is automated deployment in the cloud. So basically one-click deployment and you have multiple nodes spinning in either Amazon Cloud or VMware. This is just two starting points. Like there's Azure, there's a whole bunch of other cloud providers that we might address down the road on demand basis. These just two first on the list. We're working on centralized monitoring and management. Very important. And I got this question a lot from the people to whom I talk about this architecture. I say, yeah, there are a lot of things like that on the market, but how about security and scalability and availability? Like everything you know about security and availability of cache, you know about security and availability here. Like initially, right, security is available out of the box, all the database encryption, secured communications channel, it's there, right? For high availability, initially, our plan is to use mirroring. Down the road, it might change because within sharding architecture, you can store multiple copies of the same data in theory, right? But initially, that would be mirroring. Now, let's check out how our virtual machine is doing. So deployment is completed. I had 3 new instances of cache on my machine, master, shard 2, and shard 1. If we take a look at the time, again, virtual machine time is a bit off, but we started at 5:07 and 5:12. So about 5 minutes and 1 click to deploy shared nothing cluster of 3 nodes within a virtual machine, right? Here I'm using combination of 3 well-known, well-tested technology: Windows batch file, cache silent install, and cache installer manifest, right? Batch file, just orchestrate the whole thing. Silent install makes sure I don't have any user prompts while installation is going, so it's totally silent. And installer manifest does final configuration as the instances start. If you are to do the same, let's say on Amazon Cloud, right, you'll have the same moving parts. Instead of batch file, you would have CloudFormation script. But again, this very same machinery would kick in, and you'll be able to deploy in 5 minutes, like in fact less, because here we installing them and activating them one by one. In case of Amazon Cloud, all the shards would be installed in parallel, and then after we know IP addresses of the internal IP addresses of the shard, we can do a final configuration on the master, right? So probably even less than 5 minutes to install arbitrary complexity of shared nothing. As it is right now, you define configuration of your shared nothing cluster once, right? That's something that is frequently asked for. We're looking at the most optimal way to add or remove shards on the fly. But as it is right now, the configuration is defined once. Right, so have a little. Mirroring.
Let's say you have a master in 3 shards, and one of the shards dies in the middle of your processing. It renders the entire configuration unusable, or the other works just with the other 2 shards?
Yeah, if your mirroring configuration is up and running, what would happen is the mirror for that particular shard would kick in a few seconds, and all the processing would continue. You might get an error for that particular operation, but the whole system would survive. So what I'm doing right now is I'm creating the table on the master using all the standard tools. Okay, I'm in the wrong namespace, so yep. Namespace should be user. Yep, so we created the table. Now we invoke the loader. Okay, and loader work or not? Query. Something didn't work, but at least show plan should be apparent. So we use standard SQL to create tables with one extra keyword, right, which is short. We use standard SQL to select, to insert, update data, and so on. Though the difference is, if you look at the query plan, if that would be a single instance, what we'll see here is read the master map for your person table and one by one output the row. Here we send in results to the separate process. In fact, we send in them to the separate nodes, aggregating the data back, right, and outputting that results back to the customer. So standard SQL as is. Now, another topic is joins, and that's, again, holy grail of all these sharded architectures. First of all, join, in that particular case, it's not the syntax. So if you're scared of things like left outer join, inner join, outer join, cross join, and so on, don't worry. The only thing you need to know about joins here is we use two or more tables to produce results. Like, so syntax number 1 and syntax number 2 are functionally equivalent. Like, everyone who received the classic training in SQL, right, would say, hey, you should never use syntax number 2 because it's not apparent, not right. And it really doesn't matter. The fact is we need to touch more than one table, like, to produce results. So let's take a look at the table types that we might have as it relates to joins and sharding architecture. So as it relates to sharding architecture, sharded architecture, table can be sharded or distributed across multiple shards, or table can be non-sharded. Like in this case, the table would sit on the master and all the shards would reach to the table through ECP, right? It's actually a very good choice for some small and frequently updated tables, such as your reference tables, right? As it relates to the query, not to the sharded architecture, tables, two tables can be co-sharded or non-co-sharded. In case of co-sharded table, all the data that shard needs to satisfy the result of the query is local to that shard. Right? For instance, if you're building the database to analyze demographics for a particular geographical region, either town or zip code, you name it, most likely you'll pick, let's say, zip code as your shard key. for every single table that would be involved in this calculation. And you're doing select, show me the average house prices for this particular town, or show me the median income, right? Chart has all the data that it needs, because tables are already distributed across chart based on these geographic criteria. But if you'll try to use the same tables, same set of tables to analyze your commute pattern, who goes from which town to which for work or study, all of a sudden the same set of table became non-cosharded, because you have to reach to another node for the data. Right? So how do we process joins? So sharded and non-sharded table. Again, statement and parsed on the master. Master, in all familiar, prepares subquery, send it to the shards. Shards need tables data from both shard itself and the master. So in this connection that you have is nothing but ECP connection, where we remotely mounting the data tables from the master. And finally, master would combine results and return them. Very easy, very straightforward. Co-sharded joins, even easier. Right? We have master that receives the query. Then we have this query being sent to the shard. Shard has both tables local. Like everything I know, I need to know about my town or my set of zip codes is here, my shard. And it returns data back to the master. Master aggregates it, spits it back. So basically pretty much the same scenario as a single table select, right? The only difference, you have two tables. Yes? Exactly. In create table, you have shard is a keyword to indicate this is shard, and then optional key. And in key, you specify one or more tables that you want this data to be sharded on. The answer is on the next slide, actually. Right? So you have non-cosharded join. Again, same start, starting on the master, preparing substatements. Now, shard needs data that is located on the shard itself and the data that's located on all the other shards. We have ECP for that. So we mount all the other shards as ECP connections to that shard. We able to efficiently reach to the data. The algorithm of join itself is fairly sophisticated. It's way more sophisticated than parallel SQL join, because you want to minimize or avoid at all repeating the calculations of the same combination of rows. And we're doing that. There's a lot of effort what was put in that particular algorithm, but we have ECP and we figured out how to do that efficiently. And again, we get the results back to the client. So you can think of ECP shuffle. You have multiple shards, and every single shard connected through ECP to any other shard. Right? And we can reach to the data no matter where exactly this data is. We're doing invisible extended global references. So if you look at the configuration of this sharded system right now, you wouldn't see these connections. Other than that, if you're familiar with ECP, right, you know that this technology, it works perfectly, but it's really a pain to maintain as database administrator. You have to manually set up all these connections and so on. In shared nothing architecture, we're doing all that for you. All the configuration is done on the master. You don't lift a finger to make sure all these connections exist. right? And as a result, for this non-casharded join, we have very low overhead. There's still overhead because you have to reach to external server, but comparing to casharded join, it's very little, and that's what Robert alluded to in his presentation. So, again, there's overhead, but it's very, very reasonable. If you look at what competition is doing and what general word on the street about this situation, non-casharded join, it's their pain of distributed architecture, right? One of the competition, very advanced one, would do what they call broadcast join. They would do optimization, but the optimization would be picking their smaller table, and we're talking about 2 tables of a few terabytes in size, and broadcast it to all the other nodes in the system, right? Again, yet another quote from industry think tank, say, try hard to avoid cross-shard joins. Basically, if you're looking at the other systems on the market, you have to very carefully plan your database architecture to make sure that most, if not all, queries that you're doing are co-sharded joins. Most of the queries, right? It's not the case for shared nothing. In shared nothing, we still deliver you predictable performance for non-casharded queries. Actually, the same example as Robert was demonstrating, just the graph of the test we did internally. So here you have the response time, and here you have number of users querying the database. Once again, relatively large database, but hard cutoff was 200 milliseconds. Like no query should run more than 200 milliseconds. And as you can see, at around 40 users, we started to deviate, right? And this deviation is not sharded versus co-sharded join. It's deviation between architecture with distributed master with app server, and a single master. Right? So, again, what we figured out how to do thanks to ECP technology is predictable response time for every query. Doesn't matter sharded or non-casharded, co-sharded or non-casharded. So if I'll try to summarize what is this platform in a few words, right now it's full SQL data platform. As you heard from Robert, it would be not only SQL relatively soon, fully horizontally scalable, provides you all the security and availability that you know of cache, and gives you predictable performance for any query. Doesn't matter what shard key is, doesn't matter if table are co-sharded or non-casharded. And important disclaimer, it's work in progress, so not everything that I attempted to show you today essentially worked out of the box. If we were talking about joins, say, a month ago, I would say, a little known, by the way, outer joins are not fully implemented yet. Now they're fully implemented. So, again, work in progress. If you want to engage with us, yeah, please contact your sales team, sales engineer for participation in early adopter program. What else you can do in the conference here? Tomorrow, 11:15 in the morning, Jeff Miller right there, one of the developers along with Aviel, would be doing a flash talk about shared nothing, right? If you are on Slack, contact myself or Tom Woodfin, who acts as a product manager for this technology. Right? And we have 5 more minutes to address any questions you might have.